So far, we've been talking about limits and we've been talking a little bit about continuity and, in particular, discontinuities like vertical asymptote. And we're going to combine all of that information today and talk about limits with respect to horizontal and vertical asymptotes. So we have here that a line y equals L is called a horizontal asymptote if either the limit as x approaches infinity is L or the limit as x approaches negative infinity is L. You may have heard about a horizontal asymptote in pre-calculus or algebra 2 kind of class, that it was a line that the graph could never cross. That's not really true. The graphs can cross those lines. What we're really looking for here is the end behavior of the curve. We want to know as x gets really, really, really large, what is going to happen with our y values. And then as x approaches negative infinity, the same thing. We could have two different horizontal asymptotes here. We could have one as we go off to the right and one as we go off to the left. If we're thinking about vertical asymptotes, we're going to be looking at x as it approaches a point from either the left or the right. If one of those limits is either infinity or negative infinity, then we say that the graph has a vertical asymptote at that value. It's important when you're talking about these asymptotes to write them as equations of lines. So horizontal lines, including asymptotes, have equations in the form y equals k. And then vertical lines have equations in the form x equals k. So just when you're writing up an answer and you're talking about a horizontal line or a vertical line, make sure that you're putting the equation of the line in there. An important and useful starting point when looking at limits involving infinity is the function f of x equals 1 over x. And we can look at this and see what happens as x approaches infinity. We can look at this and see what happens as x approaches 0. One example I like to give in class is that this function is as if you had a cookie, a really large cookie, and you are in the mood to share that cookie and you would like to share it with other people. And x represents the amount of people that you are going to share the cookie with, and f of x is the fraction of cookie that each person would get. Now, if I had just one other friend and we're dividing it among two people, each person would get 1/2. If we're dividing it among the entire class, maybe 25 people, each person would get 1/25 of a cookie, which isn't all that much, but still at least a little bit satisfying. If we extend that out to all of Hazlitt High School, then we're looking at 1/900th of a cookie. And if you think about extending it, that if you would like to help out the entire world to help promote peace and prosperity, that you're going to give each person in the world a part of your cookie, you're talking about close to 8 billion people, then each person would get 1/8 billionth of a cookie. And really at that point, are they getting a cookie at all? Are they getting offended by that? I don't know what's going on with that situation. But as x gets larger and larger and larger here, as x goes to infinity, f of x is clearly going towards 0. And it's interesting with the cookie analogy that if you increase the number of cookies, if you say have 10 cookies, it starts out great. Like if you have 2 people, now they're getting 5, but inevitably we still run into that same situation. 10 cookies is not going to satisfy the entire world. Everyone is still getting a very, very, very small fraction. We're still going off to 0 as x goes to infinity. No matter how big we make that top number, that's always going to happen because x can keep getting larger and the top is finite. It's not getting any larger. And so that's a useful piece of information there to keep in mind. Also here we see as x approaches 0 from the right, f of x is going towards infinity. As we approach 0 from the left, it's going towards negative infinity. And by that definition I just gave you for vertical asymptotes, this means that there is a vertical asymptote for f of x at 0. Again, you can kind of look at what happens when we change the power on the bottom here. 1 over x squared, we're going to get to 0, and we're going to get to 0 a lot quicker. Of course, we never quite get to 0, but the limit here is 0. Notice here that as we approach 0 from either side, we're going to infinity. And so you can see that with 1 over x to the n, where n is some sort of positive value, we're always going to be going to 0 as x goes off to infinity and negative infinity, and we're going to always have this asymptote here at 0. We're going to use this, and it's going to allow us to extend into looking at limits with rational functions and other types of functions as well. We'll get to the hardcore algebra in a second here in terms of how to figure out locations of horizontal and vertical asymptotes. But I think it's helpful to look at a graph of this rational function and just kind of see what's going on. We've already talked about this here that if you have a denominator that is going to equal 0 for some value of x, there's going to be a discontinuity there. And if there's nothing that's going to cancel that out in the numerator, then it's going to be an asymptote like we have here. So if 2x minus 1 is equal to 0, we're going to have a vertical asymptote at that particular value of x, which just happens to be 1/2. And you can see that on the graph, that it wouldn't surprise anybody that 1/2 here, x equals 1/2, is going to be a vertical asymptote. In terms of the horizontal asymptote, it looks like on the graph the asymptote will be at y equals 3. And I can see here that I have a 6x and a 2x out here. These are kind of driving each part of the fraction, that as x gets really, really large, taking 2 away is pretty insignificant. I mean, if x is equal to 1, 6 minus 2, the 2 is important at that point. If x is equal to 1,000,000, all of a sudden you have 6,000,000 minus 2, and that 2 isn't quite as significant. So for very, very large values of x, what ends up happening is this function acts like 6x over 2x, which is 3. Okay, so that's a way to kind of logically think through it, and we're going to see how to apply algebra and the different limit laws next.
Got my whiteboard out here and ready to look at this function f of x. It equals 2x squared plus 9 over x squared minus 8x plus 7. And we're reminded of these two facts here, that the limit as x approaches infinity of 1 over x is 0. The limit as x approaches infinity of 1 over x squared is 0. Now, if we are talking here about vertical asymptotes, we want to do some factoring. There's no good way to factor the numerator here over the set of real numbers, but the denominator, we've got x minus 7 and x minus 1. So there are two values of x that would make the denominator 0. We've got x equals 7 and x equals 1. Neither of those factors would get canceled out by anything in the numerator. So we could declare here that x equals 7 and x equals 1 are both vertical asymptotes. And if we're thinking about horizontal asymptotes, okay, so to find the horizontal asymptotes, we're going to look at the limit here as x approaches infinity of 2x squared plus 9 over x squared minus 8x plus 7. Now, we have some limit laws that allow us to take each one of the terms in the top and the bottom and multiply them by quantity, or in this case, divide. I'm going to look at this x squared as the highest degree in either the numerator or the denominator. And what I'm going to do is divide each term by x squared. Now, if I had an x cubed floating around in there somewhere, I divide everything by x cubed. Whatever the highest degree is, that's what I'm going to work with. So when I divide each term by x squared, I have 2x squared over x squared plus 9 over x squared. And then in the denominator, x squared over x squared minus 8x over x squared plus 7 over x squared. Okay, and that's going to simplify here to the limit as x goes to infinity of 2 plus 9 over x squared. And then on the bottom here, we've got 1 minus 8 over x plus 7 over x squared. Okay, as x goes to infinity, and actually as x goes to negative infinity, the same thing is going to happen here. The 9 over the x squared, remember, it doesn't really matter what finite number is on top there. It's still going to go to 0. This is going to 0. The 7 over x squared is going to 0. And the 8 over x, they're all going to 0. And so what we're left here with is a limit of 2. Okay, and so our horizontal asymptote in this case is at y equals 2. Now, in some classes, you may have had a teacher that said, look, all you've got to do is if you have the same degree in the numerator and the denominator, you're going to take the coefficients and you're going to divide them. Like I would take 2 divided by 1 here and get 2. And that's absolutely correct. This is the logic behind why that would work. Okay, so if I have, for example, limit as x goes to infinity of 3x cubed minus 2x squared plus 5 over 6x cubed plus 4x plus 135.271 or something really bizarre, all I really need to concern myself with are these leading terms. So this is going to go to 1/2. And so that's going to tell me right away what's going on there. Now, if I have a larger degree in the bottom, what's going to happen is all of these terms in the top are going to go to 0, and it's going to make the entire limit go to 0. If I have a larger degree on the top part of my fraction, if I have a larger degree in the numerator, that's going to make this limit go towards either infinity or negative infinity. I could figure out which one by dividing the numerator by the denominator. And I also maybe out of that process could establish like a curve or a line that graph is going and getting closer to as x heads off to infinity. So that's a strategy to deal with some rational functions. Over my years of teaching this topic, there's such a huge emphasis on horizontal and vertical asymptotes that we'll spend a large amount of time in class, students will get the homework problems, and then I'll get a lot of grief the next day when they encounter something like this that has a natural log of x in it and kind of goes against those rules like, how do I divide the top by x? Or what exactly am I doing with this problem? And it involves a little bit of critical thinking here, that if I take the natural log of 2 here in the numerator, as I'm approaching 2 from the left, this numerator is going to go towards the natural log of 2. And if I think about approaching 2 from the left, okay, and I'm thinking about what kinds of numbers are going in here for x, we're looking at numbers like 1.9, 1.99, 1.999, that when I take 2 away from it, the result is going to be negative. It's going to be a negative number, and we're going to cube it. And when we cube a negative, it's still negative. Okay, and so we have a number that is negative, and it's getting closer and closer to 0 because as I keep adding 9s on there, I keep getting a number that is closer and closer to 0. So we've got a finite number on top, and we've got a negative number on the bottom that is getting closer and closer to 0. If I'm dividing by numbers that are getting closer and closer to 0, that's going to make the whole fraction get infinitely large. Now, I'm deciding here that it's going to negative infinity because, again, these are negative numbers that I'm dividing by ultimately here. Okay, now, so how would this problem change if instead we had the limit as x approached 2 from the right of the natural log of x over x minus 2 cubed? Now we're talking about putting numbers in like 2.01, 2.001. It's going to make this factor down here positive. And when we cube it, it's going to be positive. So I'm going to take natural log of 2, divide it by numbers that are getting progressively closer and closer to 0, but are positive this time. We're going to end up going towards positive infinity. So it's another limit involving infinity problem that's a little different than just dealing with a rational function.